Hey y'all, welcome back to another round of engineering. And yeah, let's get started. I have another example problem for you, and we'll just make this video short, just dealing with this problem. And yeah, what we have here are two inductors, which are being powered by some external supply not shown. Okay. So there's some external supply that has energized these inductors and has maintained them prior to the opening of the switch. And we are asked to find out what the currents are running through the circuit after the switch is opened. So why don't you go ahead, take a couple minutes, see if you can hack it out. Got it? Good. Awesome. Well, let's go at it. So the first thing that we do when we're attacking these problems is to try to figure out some initial state. Initial state. Okay. Now, generally, we choose the moment prior to the switch being opened. So I'm going to say, let's take the initial state here at the moment the switch is opened. Okay. So I'm being just a little bit, instead of taking the instant before it's opened, I'm going to take it the instant after it's open. Okay. And hopefully the reason for that will become clear in a moment. So right when the switch is open, there is a momentary, just briefly, momentary second where these inductors continue to apply or provide those currents, the 8 amps and the 4 amps. And because the switch is now open, we are going to go through the resistor branches. So the 40 ohm resistor, the 4 ohm, we've got the 15, and the 10. So let's go ahead and analyze this circuit to find out initially, the moment that that switch is open, let's go ahead and figure out what are the currents or the potentials, if you prefer, in this circuit. Okay, you got it? Well, let's see here. I'm going to attack this using, I think, node voltage. So I'm going to go ahead and call this node A. I'll go ahead and call this one B, as in boy, and I will ground that one. And so what we have here is applying for node A, we see that we have a negative 12 amps going into that node. And then coming out of that node, we have VA divided by 40 plus VA minus VB over 4 equals 0. Well, let's go ahead and do VB. We have VB minus VA over 4 plus VB. And here I'll go ahead and I'll just put in the 1 over 15 plus the 1 over 10. Okay. And that whole rigmarole equals 0. Now at this point, as we're well familiar with by now, we notice we have a set of linear equations, and so we can apply our matrix methods in order to solve. We can get the potentials VA and VB. So I will leave that up to you in order to have you, go in and plug that stuff in, and I will just give you the final answers that I had. When I plug this into my matrix and do the inversions, I get that VA and VB are, I have 96 volts and 57.6 volts. V. Now bear in mind, that's all we really need in order to figure out the initial conditions for this circuit. If we're asked to find the currents, for example, through the resistors, the initial conditions for these currents, I3, for example, we can use these values to go ahead and get those. Or if we're asked for the potential drop, the potential difference from the low and the high side, well, we've got those. So this is all we need. I'll go ahead and circle that to give us the information for the initial state of the circuit. Okay? Well, now we have a second task ahead of us, is now we need to figure out how to express the time varying part. So this is the instant that the switch is open, but now we have to figure out how do we derive the final expression for the time-dependent behavior of the circuit. And that one is going to take us a little bit longer. Ready? Here we go. So I've just copied the picture over to another slide, and let's go at it. And again, what I think I'll do is the node voltage method. Since we haven't been using that very much, I'll go ahead and try that again. Okay. And now let's go ahead and write an expression for node A. And here's the piece that's going to change is I'm interested in a generic expression, one that depends on time. Okay. So I'm not thinking just initial, that instant that the switch is opened now. I'm thinking for any time after that. And the reason I'm emphasizing that is that now I am going to use variables for the currents. Okay. Namely, I'm going to choose something like, well, we're given I1 and I2, so I'm going to go ahead and use I1 plus I2. Now you notice I've put plus signs in because of the directions indicated for I1 and I2. Okay. So I've got that. And yeah, I guess the rest of this we've already seen before. We have VA over 40. And notice I'm trying to make sure that it's obvious. I'm using lowercase v's. Okay, so it's time-dependent currents now. We have VA minus VB all over 4 equals 0. And so for the second question, or the second one, and you say, okay, Greg, I know where this is going. 4. Oh, you know what? Let's go ahead and leave these as variables. I'm leaving everything else as variables. Let's go ahead and leave these as variables too. Probably regret that later, but you never know. Okay, so R4 and VB. And again, we have this 1 over R15 plus this 1 over R10. And that whole rigmarole equals 0. Okay. Question for you. How many unknowns do I have in these two equations? Yeah. Hopefully you see it, right? We actually have 4 unknowns. For example, you can see we have both of the currents flowing through the two inductors and the node potentials. So we actually have 4 time-varying quantities here, which means we need 4 equations in order to get everything. Right? So then the question becomes, well, where do the other 2 equations come from? And it's not going to be from the node voltage. We're going to need some sort of relationship tying the potential difference to the currents, right? The potential difference from ground to A to these currents, I1 and I2. So what we have is that we do have that relationship. We know the potential drop across a inductor is related to the inductance times the change in the current. And I'll put the negative sign there. And the negative change in the current. So if the current's decreasing, then the inductor wants to increase it. And so now we see that we have the sufficient number of equations to solve our problem. We have 4 equations and 4 unknowns. Now note, before we go through and start solving, unfortunately, we see that there in these equations, we have variables, but we also have time derivatives. Okay? That means that this equation is not a linear equation anymore. The relationship between a time derivative and the actual variable is not a linear relationship. And so unfortunately, we are reduced back down to our sub and solve situation. Okay. So let me walk you through. This is going to get a little bit, I won't say hairy, but it's good. I want to tell you what we're going to do before we do it. Okay. So I'll call this equation C and D for lack of a better term. Okay. So we have a couple of different things we need to do. Number one, I am going to solve B so that we have an expression relating VB to VA. Okay. And I've just underlined there'll be some sort of constant of proportionality there. Okay. The next thing that we're going to need to do is I am going to take time derivatives of both equation B and equation A. Hopefully you can see why that is. If I want to substitute equation C and D into equation A, I need to make some sort of connection between the time derivatives. So number 3 is I'm going to take B, C, and D and sub it into A, and I will solve for the potential at A as a function of time. Number 4, I guess I'll call that 4. We'll call number 5 apply initial condition. Namely, we know that VA naught is 96 volts. Excuse me, I forgot the volt. And then lastly, we can find the currents. So this is going to take us a couple minutes. Ready? Good. Okay. So let's go for it. Some scrap paper there. So the first thing that we have is equation B. And so what equation B states is VA, and I'll work this in terms of variables for right now, R4, that's a negative, plus we have VB, and then we have this rigmarole, 3 resistors, R10 plus 1 over R15 equals 0. And so what we'll find, we have VB. Let's go ahead and find a common term, I guess. R10, R15 plus R4, R15 plus R4, R10, all over this whole rigmarole, R4, R10, R15. And that will all equal our VA divided by R4. And oh goody goody, we see that we at least cancel out one of these R's. And so at the end of the day, I won't rewrite it, but I have the expression for our relationship between VA and VB. So I'm already on to step 2. I said I would take a time derivative of it. So what we have here is the change in VA as a function of time is equal to, VB is equal to a change in VA as a function of time times this constant, R10, R15, divided by, I'll write it all out again, Don't worry, we're not going to write this out for the entire problem. I just don't want to put it down as a number. So this is really what we're going to need. We're going to need that sucker. So we'll go ahead and box that. Well, next step is we need a time derivative of equation A. And that would be di1 dt plus di2 dt plus, and I'll go ahead and I'll pull the common terms again. We have 1 over r4 plus 1 over r40. Excuse me, this is VA. And then we have a minus, and I've already taken a time derivative here, so we have a dt, we have a dv b dt of 1 over r4. That whole rigmarole equals 0. Well, now we're in a position that we can substitute in our various expressions. So from equation C, I have VA over L5, inductor 5. Then I have VA over the 20 Henry inductor. So I've got those two. Then I have this whole rigmarole, dVA, excuse me, I keep switching between capital and lowercase, dt. I've got this, I guess I'll put it as R4 plus R40 over R4 times R40. Put it like that, I guess. Right. And then I have this whole rigmarole, minus 1 over R4 and then this whole thing, R10, R15 over R10, R15 plus R4, R15 plus R4, R10. Double parenthesis equals 0. Now notice for a moment that I have managed to separate out just all of the resistor stuff, right? And also notice that these units is 1 over ohms, right? I have a resistor ohm in the numerator, I have ohm squared in the denominator. And so the total resistance here is just 1 over ohm. Okay? So what I'm going to do now is, instead of continually, perpetually rewriting this, I'm just going to take this whole rigmarole and I'm going to call it a new variable. I'll call it 1 over R EQ. So this is what I'm going to define as the equivalent resistance of the circuit. I've taken all of the resistors, I've mashed them together. This is 1 over REQ. And you can see a similar thing right over here. Notice that I could separate out just the inductors. I could have VA 1 over L5 plus 1 over L20. And I will just take that piece and define it as 1 over LEQ. That's just me being lazy, okay? But that's a very helpful thing to do at this point. I just wanted to show you that, hey, where do the equivalent resistances and inductances come out when you're doing these equations? Okay? The other nice thing is that it makes it clear what we actually need to do now. Excuse me, nose itch. So what do we have now? We have VA divided by LEQ. I apologize. What happened was I've already decided what's the high and low side when we wrote down these equations, right? VA is the high side. I've grounded the low side. And so I don't need these right now. I don't need those because I've already dictated which side's the high and low side. Okay. It's like, excuse me, I momentarily had a lapse there. So, okay, now all order is restored. Okay, so now what we have is VA dt, and we have a 1 over r EQ equals 0. Well, we know how to do this. This is a first order linear differential equation with constant coefficients. So we already know the answer to this sucker. This is separable. So we move this to the other side, and we have something that says negative REQ over LEQ, right? dt is equal to dVA over VA. And you can see why that negative sign bugged me, right? If I have that negative sign there, then all of a sudden this negative sign goes away, and I would end up with an exponential growth rather than an exponential decay. Sanity check. Okay. So the answer to this, as you are well aware by this point, is something like, okay, should be VA times equals the initial condition, e to the negative REQ over LEQ times time. So this would be something like 96 volts, e to the negative REQ divided by LEQ times t. In other words, if we plot this, it will start out time at 96 volts and rapidly die out to 0. And how it dies out is dictated by the time constant, tau, which is equivalent to LEQ divided by REQ, as we've talked about in a previous lecture. But wait, there's more, right? Now, I won't go through all of it, but recall that we are asked to find I1, for example. So now that we have the potential at node A, we are going to have to go back and use this potential to find the currents for all the other things. Oop, I ran out of space again. So for example, if we go back and look, we had something that said VA divided by L5 is equal to di1 dt. Oh no. Yeah, we're going to have to do another integral. Life goes on. This is why I gave you the problem. So what do we have here? Well, we're going to have to take our expression. So VA naught, I'll leave it like this, e to the negative REQ over LEQ times t. And then we have this inductor value in there is equal to di1. We'll put a dt in here. So we're going to have to integrate this sucker. Say from time equals 0 to some time later. And at time equals 0, the current running through I1 was 8. So there's where we're going to use that, and we'll just call this I1. So if we work our magic here, what do we find? We get a negative V, the initial potential, divided by the inductor. Then we have the our LEQ over REQ. There we go. And then we have this E to the negative REQ over LEQ t minus 1. Don't forget we're evaluating at 0, so you end up that minus 1 in there. And of course on this side we get I minus 8. Well, at the end of the day, so what happens after that? Well, the 8 goes to the other side, and we end up with something that says, oh, good gravy. We got a lot of stuff rolling around here, don't we? We have something that says 8. Move that to the other side, and I'll put, do I want a minus or a plus? I guess I'll put a plus in here, get rid of these double negatives. VA naught. We have LEQ, all divided by L5 REQ, times the quantity 1 minus e to the negative REQ over LEQ times t. And that whole rigmarole equals I1 as a function of time. Ta-da! Yeah, I know it looks messy and you got all this other stuff rolling around, but you've done it. You have found an expression for the current as a function of time. Now, one of the things to check, of course, would be the limiting cases. What happens when t is equal to 0? Well, when t is equal to 0, you get a 0 here, and so your initial current is 8. Oh, negative 8. Excuse me. Negative 8. Yeah, why does that come in? Oh, yeah. Excuse me. Remember, because of how our circuit was set up, this current is flowing in the opposite direction, right? We're told initially it's flowing 8 amps upwards, but I1 is defined as going down. So I should put a negative sign there. So this would mean positive and then negative. There we go. Yeah. So we got a negative 8 in there. Now, one of the things that seems kind of odd here is that, yeah, when time is equal to 0, everything's kosher. But it seems weird when time goes to infinity, right? That's one of the weird things, right? When time goes to infinity, the current flowing through my first inductor doesn't drop to 0, which strikes me as a little bit odd. But then I have to remember that you have those two inductors in parallel, and so some of the current is going to get directed from one inductor back to the other and back and forth. So what this is saying, the fact that as time goes to infinity, your current goes to some constant value, what it's saying is that some of that energy, a tiny portion of the initial energy stored in the inductors, stays in the inductors. Which is kind of cool, actually. So there we have it. We have the current flowing through our 5 Henry inductor. Of course, I'll leave it to you. We could follow the same process to find the current flowing through the second inductor. Okay? We would provide the exact same stuff. In fact, everything stays the same, except I would have a negative 8 plus a comma 0. This would stay LEQ, and this would be an L20 REQ. And then we'd have this whole rigmarole. If all goes according to plan. You should yell at me again. Excuse me, we're told that the second time for the second inductor, it is a 4, right? But otherwise, everything should be the same. Now, for completeness, I know this is kind of running long and arduous. For completeness, let me go ahead and you can check my algebra. So if you'd prefer to use regular numbers, well, not regular numbers, but work in terms of numbers instead of variables. What I had at the end of the day was something like 9.6 times 1 minus e to the negative 2t. And I had that minus 8. Okay. And for I2, of t. Let me check my notes here. Of course, this would be a minus 4, right? And I still have this 1 minus e to the negative 2t. So there we go. And theoretically, this should be 4 times smaller, right? Instead of doing it 9.5 divided by 5, I do it, or this 9.6 divided by 5, I'm doing it by 20. So a factor of 4. So that would mean that this should be 2.4. Also notice, just to reassert, notice that as time goes to infinity, I1 equals negative I2. Again, reasserting the idea that some of the energy gets trapped inside those two inductors, right? Pretty cool, huh? Okay, I'll leave it at that. That's a little bit longer one. So yeah, the next video, for starting off next week, we will then dive into our RLC circuits. Okay, so not putting just 2 elements, but combining all 3. And you can see how arduous this could get in terms of the differential equations. Not to worry, we'll first discuss the differential equation technique. That'll be the first thing, and you need to go through that pain, first of all, because you'll see these other places. And second of all, going through that pain will help us appreciate the next idea of complex numbers. Okay, so stay tuned. I'll get some more of those posted. Thanks for your attention. I'll see you next time.